Hello everyone, welcome to another Physics 30 example. Actually, this is not really an example, it's just a really important review of mass spectrometry. This is lesson 4 of our unit 6 on nuclear theory. So here's a schematic of a mass spectrometer. This will be the one that you have in your notes. The purpose of a mass spectrometer is essentially to use a Thomson tube device type of thing to determine some sort of characteristics about what it is that you're putting into the mass spectrometer. Normally it's the mass, funnily enough, hence the name. So you can find out the isotope, essentially, the isotope values, or the ratios of different isotopes in a sample by looking at the curvature, or the radius of curvature, as they move to this mass spectrometer, and we'll go through the details in a bit. But you can put your sample in here, whatever that might be. The sample is then accelerated and travels through the mass spectrometer, giving particular values to it that we'll discuss. It then enters a region where it starts to curve, and you can see that these two curves are obviously different. Beam 1 here has a tighter radius, a smaller radius of curvature, and that's going to be as a result of different properties of this ion. So maybe this is one type of isotope, this is another isotope, and you can then get a value of the amount of a certain isotope, and that can be useful in radiocarbon dating, for example. You can find out how old something is by the ratio of the different isotopes together. Okay, so that's essentially what's happening. Of course, schematics are just sort of simplified versions of what we're really looking at. If you want to see a real mass spectrometer, here's an example of one. It just looks like any complex lab equipment, lots of buttons and complicated things, but just to sort of show you that they are real things, and scientists will be using these all the time in labs. Okay, so let's break it up. It's a really nice section in Physics 30, this, because it brings together so many of the different concepts that we've covered so far. So we're going to break it into 3 sections. The Ion Acceleration section. So I'll just highlight that in, let's use red. So the Ion Acceleration section, you could probably figure it out from the picture, but that's this area in here. Okay, so we'll be talking about that. Then we're going to move on and we're going to talk about what's called the velocity selector. So that's the chamber next to this accelerator bit. So this is the blue section here, like this, all in here. Actually, I don't know why I coloured that top bit. Let me just get rid of that. There we go. Okay, so that's the blue section. That's the velocity selector. And then finally, as it enters the curvy bit, this is called the Ion Separation Chamber. And so that would be this section in here. Okay, so first, before we get into the sort of physics descriptions, just a couple of pieces from our notes on this. The first step is to actually produce charged particles or charged ions, and that can be done many different ways, but actually the most common way is using electron beams. So you fire electrons at a sample. This sample is normally heated, so it's kind of a gas. It's heated at the individual ions, they come into target with the electron beam. The electrons are hitting it, and what that does is, if you think back to your Bohr models, if you have a high-speed electron hitting an atom, it actually ends up knocking one of those outer electrons away. So essentially, by using electrons, kind of like almost you can think of them as billiard balls being flung at another billiard ball, the electron, and it's knocking that electron away. And by knocking it away, it becomes charged, and it's likely to be positively charged. In fact, it can be positively +1 charged, or it can be positively +2 charged. So it's important that it is charged, of course, so that it's able then to be affected by these 2 different fields as it moves through the mass spectrometer. But just note that you can have different ionized states. So if it's singly charged or singly ionized, then obviously it's going to be 1 elementary charge. If it's doubly, it's going to be 2. I guess it is possible to have triply charged ions, I suppose. That would be just less common. Okay, so we've charged our ions, we've ionized our sample, whatever that might be. And now what's going to happen is that these ions, because they're heated, it's a kind of a gas, these are going to enter this region in here. And of course you can see it's connected to a battery here, and there's going to be a positive plate on this side, a negative plate on this side. These ions are positively charged, they're going to move towards the negative plate. And if you make a little hole in the plate, they will fly through like a bullet, just like we've seen before with our electron guns and our accelerators, that type of thing. Exactly the same thing. And we can calculate that. We'll do that on the next page. We'll calculate we'll go through the statement of the acceleration here. Okay, so we can summarize. We can say the ion accelerator is basically accelerating these through a potential difference. One thing that's really important is an assumption that we are doing this from rest. That's why you can see this is arranged in such that it's vertical. So as these, even though they're not, to leave this canister, they can't be at rest, obviously, but they are at rest in terms of the horizontal displacement. And so you come back to your, your projectile motion stuff. The vertical, the up and down motion is irrelevant here. It's only the horizontal that would count for motion in terms of this linear accelerator. Okay, so they get a high speed. Great. Now they move on to the velocity selector. Okay, and so here we have two different fields at play. We have the electric field. You can see that by the arrangement of these horizontal parallel plates. Positive plate here is on top, negative is on the bottom. Of course, this is arbitrary. It can be whatever you want. But importantly, that also now means that we're going to have a magnetic field perpendicular to this electric field. And you're going to have to get your hand rules out here and figure out which direction which direction this field would be based on the arrangement of these forces. Now, crucially here, it's important to note that these accelerated charges will all be different. There'll be different velocities. And this blue region is called the velocity selector because only the ions with a certain velocity will actually remain horizontal and will neither be deflected up or deflected down. So it's probably worth mentioning that because the acceleration chamber, the red chamber, cannot produce a uniform velocity, there'll be lots of these ions that just drift all over the place. They're going to be just essentially lost to the experiment because they don't have the exact velocity. What is the exact velocity we're talking about? Well, that's going to be based on a statement that comes from a condition to do with these ions whereby the force up and the force down are exactly equal. Okay, and we'll talk about that in the next page. Okay, so we can now make a we've made a statement here about this first section. We'll make a statement about the second section. And now we're going to make a third statement about the ion separation chamber. And that is now that in this section there is only a magnetic field. But if you notice these, it's kind of not easy to see on this particular diagram, but these would be bending in a circular nature, in a circular motion. So here we can introduce the physics 20 concept of circular motion, and we can once again say that there are forces equal and opposite to each other. That is, that the force magnetic is equal to the force centripetal, and that's another statement that we can make, and we'll do that on the next page. So in summary, qualitatively, we can say in the velocity selection chamber there's both of the fields. Ions are going to enter at different speeds, but the ions with the correct speed will pass through this little hole. That's why it's a selector. Okay. In the ion separation chamber, The ions with a particular speed that made it through the velocity selector will all have the same speed now. The only field in here is the magnetic field, and it will cause them to move in circular motion. So that means we can say that this will separate out isotopes with different masses. Okay, so they'll all have the same speed, they'll all have the same charge, but what's important here is that the masses will be different, and so you can differentiate between two different masses, specifically different isotopes. And so what we haven't mentioned is this, there'll be some kind of detecting device down here, an ion detector, and you'll be able to see the appearance of these ions hitting here or hitting here. And that will give you an image. Could be a photographic film where they leave a mark, could be some kind of computer that detects it. Whatever it is, there'll be some way of detecting these collisions on this detector here. Okay, so let's get into the nitty-gritty of the physics. We'll make some statements. We're going to come up with 3 statements for these 3 different chambers. Okay, so the Ion Accelerator, remember, so there's this little process going on here where we're ionizing the sample, so these atoms are getting their electrons knocked off, they're becoming positively charged. I suppose it's possible to talk about mass spectrometry with negatively charged ions, but I think it's more common to have them positive. So anyway, here's a positive, and it's going to kind of just bubble up because it's heated up and it's a gas. We're assuming it's at rest relative to left and right motion. So this positively charged ion will just appear somewhere in the field. And it actually doesn't matter where it is, because essentially it's going to go from some state of energy to another state of energy. In other words, it's we're gonna write an energy statement. Okay, so we'll use red because this is the red section. We're going to say that the sum of energy initial is equal to, you've guessed it, the sum of energy final. And so what energy does it have when it's in the field? Well, that's like saying what type of energy does a ball have when you're holding it stationary up in the air? Well, it doesn't have any motion relative to the ground, so it has zero potential energy. It has zero kinetic energy, but it does have potential energy. It has gravitational potential energy. And so we say the same thing about this. It will have electrical potential energy. In other words, it's going to experience a force towards the negative plates. Okay, so it's going to go from, it's going to have zero kinetic energy. It's only going to have electrical energy. So I'm going to put that here, electric potential energy. It gets all the way over to the negative plate. It's going to have used up all of its potential energy, if you like. It's kind of like the ball reaching the ground. And so it will not have any electrical potential energy left, but it will have a velocity. So let's assume that it's going to go through the gap. It's going to have, at this point here, it's going to have a velocity, and we can state that in terms of kinetic energy. Okay, so essentially 100% of the potential electrical energy is converted into kinetic energy. And so, of course, we have some statements to go with that. We're going to say that this is equal to VQ, and this is equal to 1/2 mv squared. And so we're left with a statement. I said there was going to be a statement for each section. So here it is for the Ion Accelerator. We are just going to say that the velocity as it leaves this accelerating chamber, doesn't matter where it goes from, as long as it's going from rest with respect to the horizontal motion, it's going to have a velocity that is equal to the mass over 2 voltage times its charge, and the whole thing will be square rooted. All right, so this ion is leaving the accelerator. Now it's going through here with the known velocity that is equal to the mass over 2VQ square rooted. Okay, so off to stage 2. So here it goes. It's entering now a uniform electric and magnetic field. So we have an electric field. We're also going to have a magnetic field. Now, I'm just going to pause for a moment for us to figure this out. The charged ion here, of course, is traveling in this direction, so that's its velocity. And so we are going to need to use our hand rule. Now it's a positive charge, so we're going to be using our right hand rule, and we're going to get that right hand out. We're going to point our thumb in the direction of motion, which is to the right of the page, and now I need to figure out which way it's going to experience a force. And so this is where I need to think about this selector being essentially a balancing of forces. So here I'm going to just put these forces on. There must be a force upwards that is equal to the force downwards. And that's going to come from the electric field and the magnetic field. Well, it's a positive charge, so it's going to experience an electric force towards the negative plate. So that if that's negative, if that's the force electric, then this force here, this force that's going to be pushing it up, is coming from the magnetic field. So that's Fm, the force magnetic. And so this is where the palm of our hand, or the finger, if you like, the pointing direction of the right hand rule comes in. My palm is going to push upwards to represent the force, which means my fingers, the remaining fingers on my hand are all pointing into the page. So that means that the magnetic field in this case must be going into the page in order to create this condition. What condition is that? Well, that's the condition whereby the force magnetic is equal to the force electric. If you wanted to start that off as an F net, that would be good practice, because F net is the sum of all forces. Now, in terms of it going up and down, it's neither going up nor going down, because it's perfectly balanced. And in terms of forces left to right, there's no forces left to right either, because it's going at a constant velocity. In other words, the acceleration is 0. And the forces, well, the forces are going to be magnetic and electric, but because the F net is 0, one of these is positive, one of these is negative, we get the statement that we're looking for, that the force magnetic is equal to the force electric. And if we put those in, we can say the force magnetic is going to be QVB, perpendicular, and the force electric is going to be the electric field times Q. Okay, so the Q's cancel, and we're going to be left with, so the Q's are gone, so we're basically left with the velocity being equal to the electric field over the magnetic field. Okay, so that's another one of our statements. That's statement number 2. So we're on to the final stage. Here's our singly charged ion flying out of this velocity selector, perfectly horizontal. Here it is, and now it's going to go into the ion separation chamber. So let's observe the direction that the chamber is giving us. You can see here that it's curving downwards. So the ion is going to have a velocity, or a speed, I should say, that's going this way. No, velocity. That's going this way. And it's going to experience a force downwards. This electron is going to experience a force downwards, which is perpendicular to its direction. And as it starts to move, as it starts to curve, the position and the velocity will also change, which means the force will be continually pushing inwards. The force will be continually pushing to the center, essentially, of a circle. So let's represent that. I'm going to say that maybe this is the center of the circle. And as the position changes, let's represent this with dots around here. It's coming around this way, like this. As the singly charged ion is, let's say it's here, then hopefully you can see that the speed, or the velocity, is going to be sort of tangential to the circumference of the circle, which means the forces, the centripetal force, which initially was here, is now going to be here, because they have to be perpendicular to each other. That's how rules work. So this would also be the FC, and we can keep this going around. If the charged ion got to here, then we would say that the force was still towards the center of the circle and the velocity was sort of tangential, just like this. Okay, so we need to determine which direction the magnetic field is in. So this is where we get our right-hand rule out again. And in this case, we've got to represent this as the initial condition was that as the ion entered the chamber, its velocity was to the right of the page. So our right-hand thumb is going to be pointing to the right of the page. But this time, the palm of our hand is going to be down towards the bottom of the page, which means our fingers are now pointing upwards. Our fingers are pointing upwards, which means the magnetic field is going to be represented by dots. In other words, the magnetic field is coming out of the page. So this is my magnetic field. I'm just going to fill this in, making sure that it's uniform all the way through, and there's my magnetic field. Okay, so let's make our statement. We're gonna be good physics students and start with an F net. So the F net is the sum of all forces, F1 plus F2. Okay, now the mass acceleration now, because it's centripetal, it's mass times the centripetal acceleration. And that means that the centripetal acceleration times the mass is equal to the only force that's producing this circular motion. Well, we only have a magnetic field, so this must be the magnetic force. Sorry, the force magnetic. And so we can expand this out. We can say that this is now V squared M over R is equal to QVB. Okay, the velocity square and the velocity cancel out. And so we're left with a statement about the radius of the curvature. So the radius of the curvature, in other words, the distance from here to here, this radius of curvature, R, is equal to, it's going to be QB, that's the perpendicular magnetic field, perpendicular to the velocity at least, divided by V, the velocity, M. And that's a wrap. Basically, velocity selectors are using all three of these statements you might be required to talk about. So we might be able to combine them together. We might be able to talk about this. We might be able to talk about this down the bottom and this over here. It's very important that you can follow this all through. It's very important you can do the hand rules that come with it to be able to answer any qualitative questions, and it's very important you'll be able to solve for sort of radiuses, or if you were given the radius, you could solve for the mass, etc. Okay, that's it for us today. I'll see you next time.